just like with one proportion, with two proportions we also have sample size conditions that need to be met before we can assume that it's reasonable to use a normal distribution to approximate that sampling distribution. So recall from one proportion we had this condition that n times p and n times 1 minus p need to both be at least 10. Well, the good news is it's almost the exact same rule for two proportions. We now have an n1 p1 from our first sample and an n1 times 1 minus p1 from our first sample, and then we have the same exact calculations from our second sample, and the criterion is the same, but that all of these must be at least 10. Now there's a simpler way to think about this if we are given counts, because if we're estimating this from a sample, then if you multiply that proportion by the sample size, you get exactly the count that went into that proportion. So one way of thinking of this is that each count must be at least 10. To see why that's true, well, let's just back up a second to these sample statistics that we calculated. Notice that my PS hat I got by dividing my count by my sample size. Well, if I take that proportion then of 0.281 and I multiply it by the sample size, then I get back that count, right? Because I'm just doing the inverse operation there. There might be a little bit of rounding error that comes in when I back calculate it, but really this is a statement about the counts. The thing is, I have to look at the counts on both sides of what I'm counting, successes and what we would call failures. So let's look at successes and failures in this pregnancy and fertility example to see what I mean by that. If we had, for smoking women, we had 38 successes out of a total of 135, the other count that we're missing is 135 minus 38 failures. And we can see that that is 97. So these two numbers are essentially the same thing that we would get if we actually calculated n1 p1 hat and n1 1 minus p1 hat. Now if I look at non-smoking, I had 206 successes and I had 543 total, so 543 minus 206 failures. And that one should be pretty simple, 337. We can see that all of these numbers are well over 10. So we can say yes, all counts are well over 10. But make sure that you count the failures also, that you don't just look at the successes and the sample size. And if you're not sure, go ahead and calculate n1 p1 hat, n1 1 minus p1 hat. It just might be more work than looking at your successes and failures. We go ahead and just use the same condition for hypothesis tests and confidence intervals, even though technically we should be thinking about the distribution under the null hypothesis. The way that we would theoretically do that is to take that n1 and multiply it, instead of by p1, we would take it by that pooled proportion and take our n1 and multiply it by 1 minus our pooled proportion. So technically this is a slightly more accurate way to do it for hypothesis tests. and then to do the same thing with N2, or actually just to take the smaller of N1 and N2 and do this. But the reality is that it's kind of a lot of work and a lot of explanation, and in most of our samples the counts are all going to be at least 10, and that in fact this test here of the counts all being at least 10, whoops, wasn't trying to cross that out, is a little bit more conservative. So that if our data pass this, they are also going to pass this other test anyway. So don't worry about this thing I have crossed out over here in the corner. It's just something I felt like mentioning because in the case of one proportion, we do actually check these conditions slightly different from one another because of the fact that we're using the distribution under the null hypothesis whenever we're doing a hypothesis test. So feel free to use either of these, but don't hold yourself responsible for the stuff that I wrote down here in the corner and just talked about for a moment. It's sufficient to just worry about this condition right here, that each count must be at least 10, or that all 4 of these must be at least 10.